Before we launch into the double integration area, we must first have confidence in evaluating different integrals of single variable functions. Well, there are many techniques, but some of them that are commonly encountered are being considered now. A few illustrations will help you to not only understand but also use during double integrations. So the first problem that I have selected is a straightforward one. The integration of x e power x squared within the limits 1 to 2. Of course, it's not that straightforward. You'll have to think of a substitution. So we will replace x squared with a new variable, say u, take differentials on both sides. You get 2 times x dx is equal to du. And if you notice, we have x dx already. So we'll just shift the coefficient 2 to the right hand side. But that is not enough. We'll have to also change the limits of integration because the new variable u is entering the problem. So using this equation, I will derive the values of u corresponding to x is equal to 1 and x is equal to 2. For x is equal to 1, u will be 1. For x is equal to 2, u will be 2 squared, which is 4. So with these changes, let us see how this integral transforms. So I'll write I is equal to integral u from 1 to 4. E power x squared is now e power u, and x times dx is du upon 2. So we have full control over the situation now. Right, half times 1 to 4 e power u du. This is half times e power u from 1 to 4. This is half e power 4 minus e. Even though this may appear a very simple question that has been demonstrated, but these things do arise once in a way, even in double integrals. My next example will be a direct application of reduction rules that we see in the evaluation of trigonometric functions. So let us say we have an integral 0 to pi by 2 sine power 4x dx, or the integral from 0 to pi by 2 cos power 4x dx. Both of them yield the same results. You can actually see the graph of both these things to get convinced, but the sine function and the cos function in 0 to pi by 2 will have similar graphs with a shift. So without having to do both of them separately, we can directly use the direct principle. So if you recall the principle that was explained earlier, both of them produce the same result, which can be written like this. There is a numerator having 3 multiplied by 1 and the denominator 4 multiplied by 2 multiplied by something else. Now first of all, how did we write these numbers? When you have the 0 to pi by 2 integrals for sine or cos with positive integer powers, you start with a number less than that number in the numerator. 4, reduce it by 1, you get 3. Then the successive reduction by two numbers. So 3 reduces to 1. Of course, don't do the mistake of reducing further by 2. You get into a negative zone. Don't do that. And then the denominator starts with that power itself. And then again, the reduction is by 2 units. Again, don't do the mistake of extending it beyond 2 because you'll end up writing a 0. So you should never get into the negative zone, nor you should end with a 0. So it stops here. And because this is an even power, we just have to also multiply with pi. I know this is elementary stuff, but we need these things when we do problems on double integrations. So the output will be 3 pi upon 16, irrespective of whether it is a sine power 4 problem or a cos power 4 problem. My third example is what would happen when both a sine function and a cos function come together as a product in the range 0 to pi by 2. So again, there are direct principles. There is a direct principle. You first focus on the power of sine. Again, as explained before, start with one number less. So 3 minus 1 is 2. Then reduction by two numbers, but that will take you to 0. Don't do that. You can use a bracket for that. Then go to the power of cos. Start with a number less. Do a reduction by two numbers. 3 times 1. Don't go beyond that. That explains the numerator. Then the denominator, you start with the sum of these two powers. Then keep reducing 2 at a time. 7, 5, 3. 1 is also allowed, not beyond that. And now comes the main point. When you find any one of these two powers odd, as it's happening here, don't write pi by 2, you write 1. So what happens when both of them are even? You multiply with the pi by 2. Okay? So whatever is this answer, so let's see how it ends. A 3 can get cancelled here. So we are left with 2 upon 35. And not only this, suppose we swap the powers of sine and cos in the same 0 to pi by 2 range, the output is still the same. So these principles you have already learned in your lower classes, but don't forget to remember they are all very useful even now. Complexities arise when the limits are not 0 to pi by 2. So in this case, I'm taking a problem where the limits are 0 to pi. And I've taken a problem where the power of the sine function or the power of cos function is an even number. Let us say power 4 or 6 or 10 or anything like that. So whenever you have a 0 to pi integral where the power of sine or cos is even, you will get a non-zero output. So this can be reduced to a 0 to pi by 2 integral. Not only in this case, but even in the cosine case, the same thing happens. Mind you, only when the power of cos function is even, you can do 2 times 0 to pi by 2 of the cosine function. But what about the sine function? In the 0 to pi range, whether sine carries an odd power or even power, you can always write 2 times 0 to pi by 2. So the output will be the same, 2 times, as explained earlier. It is 3 multiplied by 1, 4 multiplied by 2, that's an even number. So don't forget, you should also multiply with pi by 2. So we can cancel off a 2, and then your result will be 3 pi divided by 8. Now let us add a little bit of complexity. What will happen to a 0 to pi cos power 5x dx problem. If you have heard my synopsis carefully, in the 0 to pi range, whenever cos carries an odd power, the output is straight away 0. Whereas in the 0 to pi range, sine power 5x dx can be converted as 2 times 0 to pi by 2 sine power 5x dx. You can see contrasting examples here. 0 to pi cos with an odd power, the output is 0. 0 to pi sine with an odd power is converted as 2 times 0 to pi by 2 sine power 5, and then the reduction is as before. 4 times 2, 4 multiplied by 2, 5, 3, 1, then odd power, you don't have to further multiply with 5 by 2. And 16 upon 15 is the output. In my next example, let me go to a 0 to 2 pi situation where I have, let us say, sine power 4x, but I'll make it some cos power 7x dx. In the 0 to 2 pi range, observe the power of sine and cos. Any one of them is odd. Don't waste your time. The output is 0. Remember, it happens only 0 to 2 pi. What I'm trying to tell you is 0 to 2 pi sine power 7x cos power 4x dx is also 0. So in 0 to 2 pi, whether it is cos or sine which carries an odd power, or both carry odd powers, the output is 0. Then coming to the next example, where we have integral minus pi by 2 to pi by 2. Let us say a sine power 11x problem. Of course, we don't see so many these types of questions arising in double integrations, but let us not rule out possibilities. So when you have a minus pi by 2 to pi by 2, or in general a minus k to k problem with such a situation, the output is 0 because this sin x is an odd function. Not only that, sin x to an odd power is also odd. So whenever you have an odd function from minus a to a or minus k to k, the output is just 0. But let us see what happens when you have a minus pi by 2 to pi by 2 sine power 12x dx. Now, even though sin x is odd, but sin x to the power of 12 is an even function. So you should understand the intricacies. So what if it's even? This gets converted as 2 times 0 to pi by 2 sin x power 12 dx. And the rest, the reduction rule will take care. 11, 9, 7, 5, 3, 1 upon 12, 10, 8, 6, 4, 2. Don't forget, you should also multiply with pi by 2 because it's an even power. Getting the final output is not of any great interest now, but how do you do this business is what I'm trying to explain to you. Let me now present you an example which can be solved in two different ways. The first one is generally what is considered an elementary process. The second one is a little bit involved. So if you talk about the first method, I use a substitution for the variable x . using x is equal to 4 sine square theta. What's the justification? 4 minus x would become 4 minus 4 sine square theta. That would reduce to 4 cos square theta. So it gets compacted. And you'll also see the substitution has got something to do with the limits also. So let us take differentials on both sides. You get dx is equal to 8 sine theta into cos theta. And as all before, you'll have to determine new limits, the limits for the new variable theta. Beginning with the lower limit x is equal to 0, I'll substitute in this equation. I will get 4 sine square theta is equal to 0, which would make sine theta is equal to 0. Solving that will give us theta is equal to 0. I will now take the upper limit x is equal to 4, again submit it here, and I get 4 sine square theta is equal to 4, which gives me sine theta is equal to 1. That happens when theta is pi by 2. So please remember, your work must be extremely organized whenever you do this business. The substitution, the differential, and the change of limits. So I'm going to transform this integral into a new integral 0 to pi by 2. X cubed becomes 4 sine square theta cubed into the square root of 4 minus 4 sine square theta multiplied by dx, which is 8 sine theta cos theta d theta. So you may feel the transformed integral looks more complicated than the original, but evaluation of this is easy. So let's just compile, 4 cubed into this 2, square root of 4 is 2. So you'll have 4 cubed times 2 times 8, integral 0 to pi by 2. You get sine power 6 theta there. And here you should be careful. 1 minus sine square theta becomes cos square theta. You take the square root of that, you get a cos theta. Then you still have a sine theta into cos theta d theta. So 4 cubed times 2 times 8 is 0 to pi by 2. You get sine power 7 multiplied by cos square theta d theta. A 0 to pi by 2 integral involving sine and cos will never be 0. So we'll just apply a reduction rule. 4 cubed times 2 times 8. Begin with 6. Constant reduction by 2 numbers. 6, 4, 2. Take this, reduce by 1 number. You can only do that. Now take the sum of the powers. 9, 7, 5, 3, 1. And then there is an odd power here. So don't multiply with 5 by 2. Only when both of them are even, you multiply with 5 by 2. The rest is all hand calculations, or you can use an instrument and then wind up. So this is how you get if you use element methods. Okay, that is using a substitution like this. But I have got one more approach to the same problem. What I'll do is, I'll use a substitution x is equal to 4y or 4u, anything like that. So then, differential on both sides will give me dx is equal to 4 dy. And then, the limits will change. X is equal to 0 would give me 4y is equal to 0, therefore y is 0. X is equal to 4 would give me 4y is equal to 4, so y is equal to 1. So the same problem will look like this, 0 to 1. What I mean is the new limits y is equal to 0 to 1. X cubed would become 4y cubed into 4 minus 4y into 4dy. So this would give me 4 cubed times square root of 4 is 2 times 4, 0 to 1, y cubed into 1 minus y over half times 3y. Now this would be 4 cubed times 8, and there's a special way to write this one. Y power 4 minus 1 into 1 minus y power 3 by 2 minus 1 dy. And this is where I want you to recall a very important rule that was discussed. 0 to 1, y power m minus 1 into 1 minus y power n minus 1 dy can be symbolically written as a beta function with parameters m and n. So this would be 4 cubed times 8. I hope you can now understand why this y cube has been written as y power 4 minus 1, so that this matches with this structure, and why 1 minus y power half was written as 1 minus y power 3 by 2 minus 1, because this should match with this structure. Only then m and n will be revealed. So this will be beta times m is 4, put a comma, n is 3 by 2. And you all know a beta function is converted into a gamma function using this rule. So accordingly, I am going to write this as 4 cubed times 8 into gamma 4 into gamma 3 by 2 divided by gamma, sum of these two numbers, which will give me gamma 11 by 2. And then of course you have to do some reduction here. 4 cubed times 8, gamma 4 is a 3 factorial, retain gamma 3 by 2 as it is. Reduce your gamma 11 by 2 as 9 by 2, 7 by 2, 5 by 2, 3 by 2 into gamma 3 by 2. Where is all this coming from? Don't forget, there is a rule, gamma n plus 1 is n times gamma n. So I've used this repeatedly in this situation, and you can see why I did all these things. The gamma 3 by 2 gets cancelled, and all that you need to do is simplify this result, and this will finally tally with that. So there are two ways of doing such problems. One is by the classical method, and one is using special functions called the gamma and beta functions. So dear friends, unless you are equipped at this level, you are going to face serious problems when you handle multiple integrals.